You know, people often ask me why atoms are stable. Why doesn't the electron just spiral into the nucleus and collapse? And I tell them that's the wrong question. Or rather, it's a question that reveals how deeply our classical intuitions mislead us. The electron doesn't spiral because spiraling is something a particle does when it has a trajectory, a path through space. And at the atomic scale, there is no trajectory, there is no path. These concepts, so obvious, so indispensable in our everyday world, simply don't apply. The atom exists because reality at that scale operates by rules so foreign to our experience that we can barely speak about them. And yet, we must speak about them. We have no choice. Language is all we have, even when it breaks. Let me begin with something that sounds like a contradiction, because in quantum mechanics, contradictions aren't mistakes, they're features. An electron in an atom is both a wave and a particle. Not sometimes one and sometimes the other. Not approximately one or the other. Both, simultaneously, completely. And you cannot have a full description of what's happening without using both pictures, even though they contradict each other. This is what I call complementarity. The opposite of a correct statement is a false statement, yes. But the opposite of a profound truth may well be another profound truth. And when you reach the quantum world, this stops being a clever saying and becomes the literal structure of reality. Now, I can see you frowning. You want to ask, but which is it really? Is the electron really a wave or really a particle? And here's where we must be very careful with our language. That question, which is it really, assumes there's some deeper reality beneath our observations, some objective state the electron possesses, independent of how we choose to look at it. But nature doesn't give us that. When you set up an experiment to measure wave properties, you see wave behavior. When you set up an experiment to measure particle properties, you see particle behavior. You cannot do both at once. Not because your equipment isn't good enough, but because the act of measuring one destroys the possibility of measuring the other. The electron doesn't have both properties sitting there waiting to be discovered. The properties themselves are created in the act of measurement. This sounds philosophical, I know, abstract, but it's not. It's the most practical, most tested, most brutally confirmed fact in all of physics. Every transistor, in every computer chip, in every device you own, works because of quantum tunneling. Because electrons behave as waves and pass through barriers they shouldn't be able to cross as particles. Every laser, every LED, every atomic clock, every MRI machine, they all depend on this wave-particle duality being true, not approximately true. Exactly true. The entire technological foundation of modern civilization rests on principles that violate common sense. So when I say the electron is both wave and particle, I'm not being poetic, I'm being precise. But let's go deeper. Let's talk about what an atom actually is, because this is where everything becomes strange. In classical physics, an electron orbiting a nucleus is like a planet orbiting the sun. It has a position, a velocity, a definite path through space. But here's the problem. An accelerating electric charge radiates energy, always. This is Maxwell's equations, ironclad classical electromagnetism. So an electron orbiting a nucleus is constantly accelerating, constantly changing direction, which means it should constantly radiate energy. And as it loses energy, it should spiral inward faster and faster until it crashes into the nucleus in about a trillionth of a second. Every atom in the universe should collapse instantly. You shouldn't exist, I shouldn't exist. Nothing should exist. And yet, here we are. Atoms are stable. They've been stable for billions of years. So something in our understanding is catastrophically wrong. The question is, what? And the answer that took decades to understand is that the electron isn't orbiting at all. Not in any classical sense. It doesn't have a position and a velocity simultaneously. It doesn't follow a path. Instead, it exists in what we call a quantum state, described by a wave function that spreads throughout space around the nucleus. You can think of it as a cloud of probability, if you like, though that metaphor will mislead you if you push it too far. The electron isn't somewhere in the cloud. The cloud is the electron as much as anything at that scale. Now here's where complementarity becomes essential. If you measure the electron's position, if you ask, where is it right now, the wave function collapses and you get a definite answer. You find the electron at a specific point. But the moment you've measured its position precisely, you've destroyed all information about its momentum. You can't know where it's going anymore. Conversely, if you measure its momentum precisely, you lose all information about where it is. This isn't a limitation of your measuring device. This is nature telling you that position and momentum cannot both have definite values at the same time. The electron doesn't have a simultaneous position and momentum waiting to be discovered. It has one or the other, depending on what you choose to measure. Both descriptions are necessary. Neither is complete. And that's not a flaw in our theory. That's the structure of reality itself. You see, we built our language in a world of rocks and rivers and trees, objects with definite positions and speeds, things that follow trajectories we can predict. And that language works beautifully for everything we encounter in daily life. But it was never designed for atoms. It was never designed for a realm where the very act of observation changes what you're observing, where properties don't exist until you measure them, where asking, what is the electron doing when I'm not looking, is like asking, what is the sound of one hand clapping? It's not that we don't know the answer. It's that the question itself is meaningless. Let me give you a concrete example, something you can actually picture. The double-slit experiment. You take a source of electrons and a barrier with two narrow slits in it. You fire electrons at the barrier one at a time. On the other side, you have a screen that lights up wherever an electron hits. Now, if electrons were simply particles, little bullets, following definite paths, you'd expect to see two bright bands on the screen, one behind each slit. Each electron goes to one slit or the other, and you get two clusters of hits. Simple, classical, intuitive. But that's not what happens. Instead, you see an interference pattern, many alternating bright and dark bands, exactly like the pattern light waves make when they pass through two slits and interfere with each other. The electron somehow is going through both slits simultaneously and interfering with itself. Now, you might think, maybe there's something wrong with the experiment. Maybe the electrons are bouncing off each other. So you slow down the rate until you're firing one electron at a time, with seconds between each one. Same result. The interference pattern builds up gradually, electron by electron. Each single electron, traveling alone, is somehow sensing both slits. It's behaving as a wave. But here's where it gets truly strange. You decide to figure out which slits each electron actually goes through. You put detectors at the slits to watch. And the moment you measure which path the electron takes, the interference pattern disappears. Now you just get two bands, exactly what you'd expect from particles. By observing, by gaining information about the electron's path, you've changed its behavior fundamentally. You've forced it to be a particle instead of a wave. Both descriptions are correct. The electron as a wave, spreading through both slits, interfering with itself. That's one complementary picture. The electron as a particle going through one slit or the other with a definite path is another. You can see one or the other, never both at once. And you decide which one you see by how you choose to set up your measurement. This isn't philosophy. This is experimental fact, confirmed millions of times, with electrons, photons, atoms, even large molecules. Nature herself operates by complementarity. Reality at the quantum scale doesn't exist independently of observation. The observer and the observed are fundamentally inseparable. Now let's return to the atom and why it's stable. The classical picture electron orbiting nucleus fails completely, as we've seen. But the quantum picture succeeds. The electron exists in a standing wave pattern around the nucleus, a stable configuration that doesn't radiate energy because it's not accelerating, it's not moving in the classical sense at all. It exists in a quantum state with a definite energy. And here's the crucial part. These states are quantized. The electron can only exist in certain specific energy levels, not anywhere in between. It's like a guitar string that can vibrate at certain frequencies. The fundamental, the first harmonic, the second harmonic, but nothing in between. We can't have half a vibration. Similarly, you can't have an electron halfway between energy levels. It's in one level or another, period. This quantization is what prevents the collapse. The electron in the lowest energy state, the ground state, can't radiate energy and spiral inward because there's nowhere lower to go. It's already at the bottom. It's stable not because some force is holding it up, but because quantum mechanics forbids it from being anywhere else. The atom exists because reality itself is discrete, quantized, fundamentally different from the smooth continuum we experience in everyday life. In this discreteness, this quantization comes directly from the wave nature of matter. Just as a wave on a string can only form certain patterns, the electron wave around the nucleus can only exist in certain configurations. Both descriptions, wave and state, are needed. Neither alone captures the full picture, but there's something deeper here, something that goes beyond atoms and into the nature of knowledge itself. When I say the electron doesn't have a position until you measure it, I'm not saying we don't know where it is. I'm saying where it is doesn't exist as a definite fact in nature until the measurement happens. Before measurement, the electron exists in a superposition at quantum state that's a combination of multiple possibilities. It's not in one place or another, with us just ignorant of which. It's in a state that includes all possible positions with different probabilities. Only when you measure does the superposition collapse into one definite outcome, and which outcome you get is genuinely random. Not pseudo-random, not deterministically unpredictable like weather, but fundamentally, irreducibly random. Nature herself uses dice. This disturbed Einstein enormously. He felt there must be some deeper theory, some hidden variables underneath quantum mechanics that would restore determinism and objective reality. He famously said God does not play dice with the universe. And I had to tell him, Einstein, stop telling God what to do. The evidence is overwhelming. Experiments have been done. Bell's theorem, quantum entanglement, tests that Einstein himself helped design. And they all confirm the same thing. There are no hidden variables. The randomness is real. The complementarity is real. Reality at the quantum scale is genuinely, irreducibly indeterminate until the moment of measurement. Now, does this mean reality doesn't exist when we're not looking? That's a natural question, but again, it's a question that imports classical assumptions into a quantum context. Reality exists. Atoms are real. Electrons are real, but they don't exist in the way a rock exists. They don't have all properties defined at all times. They exist in quantum states that contain potentialities, not actualities. When you measure, one potentiality becomes actuality. Before measurement, asking what is the definite value is like asking what is north of the North Pole. The question assumes a conceptual framework that doesn't apply. Let me try another approach. Imagine you're flipping a coin, but it's a quantum coin. While it's in the air, it's not heads or tails. It's in a superposition of both. And I don't mean you don't know which it is. I mean it genuinely is both, in a state that can only be described as heads plus tails divided by the square root of 2, if we want to be mathematically precise. This superposition is a real physical state with real physical consequences. You could, in principle, make two quantum coins interfere with each other, just like waves. But the moment the coin lands, the moment you observe it, the superposition collapses, it becomes definitely heads or definitely tails. The act of measurement forces nature to choose. This is what happens in the atom. The electron isn't in a definite state until you measure it, but it's not in an indefinite state in the sense of vague or fuzzy. It's in a superposition, a precise, mathematically describable quantum state that contains multiple classical possibilities. And when you measure, you get one outcome with a probability determined by the wave function. The wave function itself evolves deterministically according to Schrödinger's equation. It's only the collapse, the moment of measurement, that introduces randomness. Both aspects are essential: deterministic evolution of possibilities and random selection of actualities. Both are needed to describe what happens. Neither alone is sufficient. Now here's something remarkable. This framework, this Copenhagen interpretation, as it's come to be called, has been tested in ways that would have seemed impossible when we first developed it. Quantum computers manipulate superpositions directly, using the fact that the quantum bits can be both 0 and 1 simultaneously to perform calculations that would take classical computers billions of years. Quantum encryption uses entanglement two particles in a shared superposition to create codes that are physically impossible to break without being detected. GPS satellites require corrections for quantum mechanical effects on atomic clocks. The entire semiconductor industry, everything from solar panels to smartphones, depends on quantum tunneling and energy quantization. This isn't abstract theory. This is engineering. This is the bedrock of modern technology. And yet, even after a century, people still ask, but what's really happening? What's the electron really doing? And I have to say, you're asking for a classical answer to a quantum question. You want me to tell you a story about particles following paths, about objects with definite properties existing independently of observation. But nature doesn't work that way. The best I can do, the most honest thing I can say, is that the electron exists in a quantum state described by a wave function, and when you measure, you collapse that state into one of several possible outcomes. Both the wave description and the particle description are aspects of this deeper quantum reality. Both are true. Both are needed. And if that seems paradoxical, contradictory, impossible to visualize, yes, exactly, you've understood it correctly. There's a certain humility required here, a recognition that nature is under no obligation to make sense to creatures who evolved to chase prey across grasslands. Our intuitions were shaped by natural selection to deal with medium-sized objects moving at medium speeds, not atoms and electrons. At the quantum scale, reality simply is different from what we expect. Position and momentum can't both be definite. Wave and particle are complementary aspects. Properties don't exist until measured. These aren't failures of understanding, they're discoveries about the deep structure of nature, and accepting them requires letting go of the idea that reality must conform to our everyday experience. But here's what I find most profound. Quantum mechanics doesn't just describe atoms, it describes the boundary of what can be known. It reveals that there are limits to knowledge not because we're ignorant, but because nature herself doesn't contain the answers to certain questions. If you ask what is the electron's exact position and momentum right now, nature says that question has no answer. Not I won't tell you, but there is no such thing. The universe doesn't store that information because storing it would be inconsistent with how the universe operates. This is a deeper kind of limit than we've ever encountered before. It's not a practical limit like the speed of light. It's not a technical limit like the resolution of microscopes. It's a fundamental limit on reality itself. And this changes everything about how we think about science and knowledge. For centuries, we believed that the universe had definite properties, and our job as scientists was to discover them. The universe was out there, objective and independent, and we were passive observers recording facts. But quantum mechanics tells us no. The observer and the observed are inseparable. The properties you measure depend on how you choose to measure them. You cannot stand outside nature looking in. You are part of nature, and your interaction with what you measure is part of the phenomenon itself. This doesn't mean science is subjective or the truth is relative. The predictions of quantum mechanics are objective and precise, but it does mean that reality is not a collection of definite facts waiting to be discovered. It's a web of potentialities that become actual through interaction and observation. Every atom in your body, every molecule, every chemical reaction that keeps you alive operates according to these quantum principles. The stability of matter, the structure of DNA, the way enzymes work, the functioning of your eyes and brain, all of it depends on quantum mechanics being exactly right. You are a quantum system built from quantum systems sustained by quantum processes. And yet your experience, your conscious perception, is entirely classical. You don't perceive superpositions. You don't sense complementarity. You see definite objects in definite places. Why? How does the quantum world give rise to the classical world of our experience? That's still a deep mystery. Some call it the measurement problem. Some call it the quantum classical transition. It's perhaps the most profound unanswered question in physics. My approach has always been pragmatic. Quantum mechanics works. It makes predictions, and those predictions are confirmed. We can use it to manipulate atoms, to build technologies, to understand chemistry and biology and cosmology. Whether there's some deeper reality underneath, some ultimate explanation for why nature is quantum, I don't know. Maybe that question is beyond physics. Maybe it's a question for philosophy or metaphysics. What I do know is that quantum mechanics is complete as a physical theory. It describes everything we can measure about quantum systems. And if you ask for more then, that if you want to know what's really happening in some ultimate metaphysics can answer that. Physics can't answer that. Physics describes measurements and predictions, relationships between observations. It doesn't claim to describe reality independent of our possible observation, because such a description may be meaningless. This is complementarity at its deepest level. We need classical concepts to describe our measurements and experiments, because that's the language we have. But those classical concepts are inadequate to describe what's happening at the quantum level. We're trapped using tools designed for one domain to talk about another domain, where those tools don't quite fit. And yet, we must use them because we have no other language. This doesn't make quantum mechanics vague or imprecise. The mathematics is exact, the predictions are sharp. With translating that mathematics into words, into pictures, into intuitive understanding, that's where we hit the limits of language itself. So when students ask me how to visualize an electron in an atom, I tell them, don't try to visualize it in the way you visualize a ball. That's not what an electron is. Instead, learn to think in terms of quantum states, wave functions, probability, amplitudes. Learn to accept that nature is described by mathematics that doesn't have a simple visual representation. The wave function is real. It has physical effects. It evolves according to laws. It determines what we measure. But it's not a physical wave in space like a water wave. It's a more abstract kind of wave, a wave of probability amplitude in an abstract space. And yes, that's difficult to picture. That's exactly the point. Reality at the quantum scale doesn't look like anything, because looking is a classical concept that involves definite positions and trajectories. Quantum reality is what you calculate and measure, not what you see in your mind's eye. But despite all this abstraction, despite all this departure from intuition, quantum mechanics brought us back to something ancient, discreteness. The idea that nature comes in irreducible units, that there's a smallest amount of something, that reality is granular rather than smooth. The Greeks speculated about atoms as indivisible units. They were right, though not in the way they imagined. Matter is made of atoms, yes, but atoms themselves are quantum systems, and energy comes in discrete quanta, and even space and time might be discrete at the Planck scale. Nature's continuity, the smooth flow of classical physics, is an illusion that emerges when you average over vast numbers of quantum events. At the foundation, everything is quantized, everything comes in units, everything is fundamentally discrete. And this discreteness is what allows atoms to exist. If energy were continuous, electrons could spiral smoothly into nuclei, radiating arbitrary amounts of energy at arbitrary rates. But energy is quantized. The electron can only emit or absorb specific amounts, jumping between specific levels. And at the lowest level, there's nowhere left to go. The atom is stable because quantum mechanics forbids continuous collapse. The electron wave is confined to specific standing patterns, specific modes, specific energy states. It can't exist anywhere else. The math doesn't allow it. Nature doesn't permit it. This is perhaps the most remarkable thing. Reality enforces its own rules so strictly that atoms cannot not exist. Even the laws of quantum mechanics, given the quantization of energy and the wave nature of matter, atoms must form and must be stable. It's not some delicate balance, some lucky coincidence. It's inevitable. The universe couldn't be made of anything else. Helical physics predicts universal collapse. Quantum mechanics predicts stable atoms. We exist because quantum mechanics is true. Now, you might wonder, why these laws? Why quantum mechanics rather than classical physics? Why does nature use complex numbers in the wave function? Why the specific form of Schrödinger's equation? Why this particular set of rules rather than some other set? I don't know. Nobody knows. These are the laws we discover by experiment. We can ask why they work. We can check them against observation, test their predictions, verify their consistency. But asking why they're true rather than something else that may be a question physics cannot answer. It may be like asking why there's something rather than nothing. At some point, you reach foundations that simply are, and explanation must stop somewhere. What I can tell you is that these laws, strange as they are deeply beautiful. There's an elegance to the mathematics, a unity to the framework, a sense that it all fits together in a way that feels, I don't know how else to say it right. When you derive the energy levels of hydrogen from first principles using quantum mechanics and they match the spectral lines exactly, when you calculate the magnetic moment of the electron and it agrees with the experiment to 10 decimal places, when you predict the existence of antimatter and then someone discovers this, there's a sense of awe. Not just that we can describe nature mathematically, but that nature seems to be mathematical at its core. And yet, with all our success, with all our precision, with all our technological mastery, we are left with profound puzzles. Why does measurement collapse the wave function? What counts as a measurement? Does it require a conscious observer, or is any interaction sufficient? How does the classical world emerge from quantum foundations? Are there limits to superposition? Can you put a cat, a person, a planet in a quantum superposition, or is there a size limit? These questions remain open, debated, mysterious. Quantum mechanics is complete as a calculation or tool, but as a picture of reality, it raises as many questions as it answers. Some find this frustrating. They want certainty, clarity, the definite picture of how things are, but I find it liberating. We've reached the boundary of what can be known, and instead of anti-ignorance, we found structured mystery. We have a precise mathematical framework that describes everything we can measure, even if it doesn't satisfy our intuitive desire for visualizable mechanisms. We've learned that nature is stranger, subtler, more elusive than we imagined. And in that strangeness, there's room for wonder. Physics has given us enormous power. We can split atoms, create new elements, manipulate individual quantum states. But it has also shown us humility. We cannot know everything. We cannot observe without disturbing. We cannot separate ourselves from what we study. We are not gods looking down on nature from outside. We are part of nature, entangled with it, complicit in creating the very phenomena we measure. And perhaps that's the deepest lesson of quantum mechanics. The subject and object, the observer and observed, the knower and the known, these are not separate. They are complementary aspects of a single, irreducible whole. So when you ask me why atoms exist, I can give you the quantum mechanical answer, because electrons form standing wave patterns around nuclei with quantized energies and lowest states that cannot decay further. But the real answer, the deeper answer, is that atoms exist, because reality at small scales is quantum, because properties are complementary, because observation creates facts that didn't exist before measurement, because nature herself operates by rules that defy classical intuition, yet work with perfect precision. Atoms exist because the universe is fundamentally quantum, and we exist, you and I, having this conversation because atoms exist. That's the chain of necessity. Quantum mechanics makes atoms stable. Stable atoms make chemistry possible. Chemistry makes life possible. Life makes consciousness possible. Consciousness makes physics possible. And physicists discover quantum mechanics. The universe has arranged itself in such a way that it can understand itself. And the understanding we've reached, complementarity, superposition, quantization, the limits of knowledge, these aren't just facts about electrons. They're insights into the nature of reality itself, into what it means for anything to exist, to be knowable, to be real. And as this seems strange, paradoxical, difficult to grasp good, that means you are thinking about it correctly. As I've often said, anyone who is not shocked by quantum mechanics has not understood it. The shock, the confusion, the sense that something profound has been revealed, that's not a bug, that's a feature. Nature is showing you her deep structure, and it's nothing like the surface appearances you're used to. Both descriptions are needed. Classical and quantum, wave and particle, deterministic and random. Neither is complete alone. And that incompleteness, that necessary complementarity, that's not a flaw in our understanding, that's the shape of reality itself. You know, we've built a civilization on these principles. Every computer, every phone, every medical scanner, every precision instrument relies on quantum mechanics being exactly correct. The theory works, it predicts, it explains, it empowers, but it also humbles. It shows us that nature is graspable but not visualizable, describable but not picturable, knowable but not completely. We can ask questions and get answers, but only certain questions have answers. Others like, what is the electron really doing when I'm not measuring it? Those questions resolve upon examination. They assume a framework that nature doesn't use. And maybe that's fitting. The universe doesn't owe us intuitive explanations. It doesn't have to make sense in terms of our evolved categories of thought. What's remarkable is that we can understand it at all that mathematics works, that experiments agree with theory, that quantum mechanics gives us a framework powerful enough to predict and manipulate the atomic world, even if it never feels quite natural, quite comfortable, quite visualizable. So atoms exist because quantum mechanics is true. And quantum mechanics is true because that's how nature works. Not because it's easy to understand, not because it fits our preconceptions, but because experiment after experiment confirms it. Because every alternative we've tried fails. Because complementarity, for all its strangeness, is the only framework that accommodates the full range of phenomena we observe. Wave and particle, position and momentum, deterministic evolution and random collapse, both sides of each pair are needed. Reality demands contradiction. Truth requires paradox. And understanding means accepting what nature shows us, even when it violates every intuition we have. That's what I discovered about atoms, that they exist. Because reality at small scales is irreducibly quantum. Because observation and reality are inseparable. Because properties are complementary rather than definite. Because nature uses superposition and quantization and fundamental randomness. Not because I wanted it to be that way. Not because it's philosophically satisfying or easy to teach or comfortable to believe. But because that's what the evidence demands. That's what experiment reveals. That's what nature is. And if you followed me this far, if you've stayed with me through all these paradoxes and contradictions, through wave functions and complementarity and the limits of knowledge, then you understand something profound. Not just about atoms, but about reality itself. About how strange it is, how beautiful it is, how stubbornly it refuses to conform to our expectations. About how science isn't about confirming what we already believe, but about discovering what actually is, no matter how alien it seems. The atom exists. You exist. Quantum mechanics is why. And the reason quantum mechanics works is something we may never fully grasp. We can describe it mathematically, predict with it precisely, build technologies upon it reliably. But explaining why nature chose these rules rather than others that may be beyond physics entirely. It may be a question for metaphysics or theology, or perhaps no answer exists at all. What we have is this: a framework that works, a theory that predicts, a mathematics that matches measurement. We have complementarity as a principle, observation as a creative act, superposition as a real physical state. We have atoms that are stable, matter that persists, a universe that exists long enough for us to study it. And we have the humbling knowledge that reality doesn't end where our understanding ends. That there are questions we cannot answer, not because we lack information, but because the questions themselves transcend the framework of inquiry. Physics has taken us to the edge of the knowable. It's shown us the boundary. And on this side of the boundary, within the realm of what can be measured and calculated and predicted, we have quantum mechanics. We have a complete theory. We have answers. Beyond the boundary, in the realm of ultimate wise and absolute truth there, perhaps, silence is the only honest response